billionaires from paying tax for a living. I think we can all agree that I've improved my standing in the world. So what I'm going to talk to you about is gravitational lensing, which I'm sure some of you will have heard about already. But if you haven't, don't worry. It's really cool and really fun and involves an awful lot of pretty pictures. So gravitational lensing is a side effect of Einstein's theory of general relativity. So one of our first questions tonight was, general relativity is a theory of what? Any answers?
Gravity.
Gravity, there we go, that wasn't so hard. What I do is I use this byproduct of general relativity, gravitational lensing, to look at galaxies very, very far away. Now, as I'm sure you all know, the further away something is, the longer it's taken the light to get to us. So if you look at stars in the sky, you see them as they were a few years ago. You look at some of our nearest galaxies, you're looking more like a few million years into the past. That's all yesterday as far as I'm concerned. Anything that you can see with your eyes or even with a small telescope is far too close for me to be interested in it. I'm interested in looking at galaxies that are so far away, we're seeing them almost all the way back to the beginning of time. And the reason this is cool is, first of all, because we can, and astrophysicists are really into their superlatives. We all want the biggest, the brightest, or in my case, the furthest away. But what this is enabling us to do is actually see galaxies in the early stages of evolution, right at the beginning of time. And we can piece that together with galaxies that we see further along in their evolution, and then get a picture of how these galaxies actually formed. So what I actually do for a living, literally, is I look at things that happened a long time ago in a galaxy far, far away. No sound? What? Okay, can everyone sing the Star Wars music? There we go. Better late than never.
Good.
So, Star Wars references are kind of compulsory at the moment, but I'm a Trekkie, so I just want to point out that I'm wearing the Enterprise on my dress. So, what general relativity is a completely new way of thinking about how gravity works. Under Newton's gravity, everything is attracted to everything else that has mass. And this is kind of problematic if you try and think about how it works, because everything just knows about things that are far away. And so there's this kind of spooky action at a distance thing going on that doesn't really sit well with us. So what Einstein came up with is, instead of space just being this empty place in which stuff in the universe happens, space is actually affected by the matter in the universe and affects matter in turn. So this is a flat representation of space, and if something's moving through it, it moves in a straight line. So far, so obvious. You then introduce mass into this, and it's curving the fabric of space. So now if something tries to move past that mass, it's going to follow a curved path. It still thinks it's moving in a straight line, but space itself is curved, so it moves in a curve. Now, depending on how fast it's moving, it might get trapped in there. You can imagine it getting attracted towards that big bit of mass, let's call it a star, and it will start to move then around in circles. And this is why the Earth orbits the Sun, it's why the Moon orbits the Earth, why the Sun orbits the center of the galaxy. All of these things think they're moving in a straight line through space, but the space is curved, so they keep falling towards the object that they're orbiting, but constantly missing, hence they stay in orbit. Now, the way this is usually demonstrated is with a trampoline, because trampolines are fun. We were going to have a trampoline here tonight, and that fell through, so now I have a video of a trampoline. It's the same, right? So this was put together by Lara Akins and Professor Pawan Kumar at the University of Texas at Austin. And you can see a big glowy sun and a little tennis ball that's orbiting around it. Now, what's wrong with this demonstration? The tennis ball crashes into the sun, right? So that's not how gravity works. And this is why a lot of people get confused. Like, they've seen this explanation of general relativity a lot, and it doesn't help them conceptualize what's going on. And the reason is that this is a flawed analogy. The trampoline is being bent by the object you put on top of it because of gravity. So gravity is pulling it down, but you're using that to demonstrate gravity. So in the real world, the curvature is gravity. There's no extra force pulling things down. So that's why things don't exactly move the same way as they do on a trampoline. But the basic principle is right. You roll a ball across a curved trampoline, it's going to follow a curved path, and this is the same in space. So what's really interesting from my point of view is this is not just true for matter, like the moon and the earth, the sun, whatever. It's also true for light. If light is moving past a very massive object, the path of the light gets curved as well. And this is what gives us what we call gravitational lensing. And that brings me to another question. If you want to demonstrate that general relativity is real, when would you measure the positions of stars?
Total solar eclipse.
Total solar eclipse. That's correct. And the reason is, if you observe stars normally, now imagine your solar system, so say the sun is over here, I'm the Earth, and when I'm facing this way, I'm looking towards the sun, so I'm not seeing any stars. I can only see the stars that are on this side of me. To see the stars that are over there, I've got to wait 6 months until I'm the other side of the sun, and then I can see those stars. Right, that's why we see different stars at different times of the year. But what if you could see the stars over here while you're looking past the sun? Then those stars have followed a path that involves going past something massive, the sun, which they don't do normally when you see them in 6 months' time, or 6 months ago. So take these stars here. We introduce the sun. This is what happens. This is hugely exaggerated, obviously. But the stars will all appear to move outwards from the position of the sun. Of course, you can't actually observe that because the sun's in the way, and the sun is a lot brighter than these other stars. So you do it during a solar eclipse. I really enjoy PowerPoint animations, if you can't tell. And then during the eclipse, you can see these stars that you wouldn't normally see, and therefore measure that they've changed their positions relative to where they would normally be. Now, Newtonian gravity predicts this as well, but the case in Einstein's general relativity is the apparent movement of these stars is about double what you would normally expect. So when Einstein first published his theory of general relativity in 1915, so it was about 100 years ago, people wanted to test whether it was real, and the obvious test was to do this. So 1919 was the next total solar eclipse. A bunch of people set off to 2 locations, most famous of which was an island off the west coast of Africa, in order to measure positions of stars during an eclipse. And they measured this movement. The stars were not where they would normally be. And this was the headline in the New York Times the next day. There's no hyperbole in that at all. I really like men of science more or less agog over results of eclipse observations. I think this is better than nowadays whenever anything weird happens in science or the newspapers say we're baffled. I'd rather be agog. Obviously the women of science completely understood what was going on. So this happened in 1919. Pretty much overnight, Einstein became a celebrity. So pretty much the reason you've heard of Einstein was because this happened. Within like a year, there was something like 100 books on general relativity, and it became accepted very quickly. However, Einstein did not propose the thing that I do with gravitational lensing. This was another one of our questions tonight, was who first proposed using galaxies as gravitational lenses to view distant objects? Does anyone know? That's hard. I was under the impression that you were going to have seen the talk before answering the questions, and that's why they're hard. It would be really trivially easy if you had already seen the talk first. So, did I hear the right answer? Close, yes. Fritz Zwicky. This is like one of my favorite astronomers of all time, Fritz Zwicky. He doesn't get enough credit. He was an absolute genius. He was one of those people who he kind of carpet bombed amazing weird ideas, and occasionally something hits. He also had plenty of crazy ideas that were nonsense. He came up with this thing that was to do with sending rockets underground to fire at cities. Luckily that didn't pan out. But his ideas about gravitational lensing were pretty spot on. Incidentally, this thing he's doing here is very famous. He likes to refer to astronomers who he generally didn't get on very well with as spherical bastards, because no matter which way you look at them, they're bastards. And he had some really, really insightful ideas. He was, among other things, the first to coin the phrase dark matter. He did it in a paper that's in German, so he doesn't often get credited with it, but it's there. And gravitational lensing, this is really cool. I'll highlight the relevant quote. I can't read it on my screen. So he says, I made some calculations which show that the extragalactic nebulae offer a much better chance than stars for the observation of gravitational lens effects. Now, when I showed you my animation of the stars during a solar eclipse, I said it's exaggerated. It was extremely exaggerated. The measurements, the movements rather, are so tiny that it's extremely difficult to measure. And actually, if you go back and look at the data that Eddington and co. got in 1919, they did not conclusively prove that the stars had moved. Their equipment was not sensitive enough. They just really wanted it to be true. And sadly, that's the thing that happens in science a lot. But it turns out other people went back later with better equipment and it was right, so they got away with it. They get to keep the credit. And then those were really nearby stars. So observing this effect with anything else is going to be really difficult. And the reason is that your gravitational lens is the sun. And the sun is pretty massive compared to us, but on a cosmological scale, it's pretty tiny. So what you want is something much more massive than that. So Fritz Zwicky came up with this in the 1930s, and this was only a few years after galaxies had been discovered. He refers to them as extragalactic nebulae, and that was the word for galaxies. And they'd been observed for 100 years or so, these kind of spiral things in the sky, and no one really knew what they were. They could be galaxies. This is entire collections of hundreds of billions of stars. They could equally well just be a star with some kind of dusty disk around it, maybe forming a solar system. The only way you can tell those apart is obviously they're vastly different scales, so you have to know how far away they are. And the way to determine the distance to these things was only discovered in 1929. Well, the method was discovered in 1917 by Henrietta Swan Leavitt. Hubble takes all the credit for that. He just used the method and was able to determine that Andromeda was this whole other galaxy outside of our own. So therefore, only a few years after we realized that we lived in this huge universe with all these island universes in it, Zwicky came up with this idea of using them as lenses. And later on in this paper, he says, it would enable us to see nebulae at distances greater than those ordinarily reached by even the greatest telescopes. Now, it might not seem obvious why, so I'm going to demonstrate why gravitational lensing is more than just a kooky side effect of general relativity. So let's imagine that we're observing with the Hubble Space Telescope, and we're looking at the Whirlpool galaxy, but it's really, really far away. So that light that comes towards us spreads everywhere, and we only get the bit that's directed towards us. But as it gets curved past, say, a cluster of galaxies, more of that light's being focused in our direction. So light that would ordinarily get scattered far away from us is directed towards us. We therefore get more light. This means that the distant galaxies are magnified. Now, if you look at this diagram, which is obviously a very toy model, how many multiple images would you say are formed every time you see a distant galaxy like this? And the answer is just even or odd.
Odd. Even.
It's odd. The reason is you've got the light can go in either direction past something massive. So in this case, I've shown a galaxy cluster called Abell 2744 that we're going to become very good friends with later. And it doesn't have a preferred direction, so it can go either way, so you get two images on either side. Because space is three-dimensional, sometimes that happens up and down as well as side to side. But it also goes straight through the middle. And this is the one a lot of people often forget. This one here, that goes straight through the middle of the cluster, is often demagnified, so it actually appears fainter than it normally would. And also, because it's going straight through the center of the thing that's doing the lensing, it's often hidden by the thing in the middle, so you never see it. But there are actually always an odd number of these images. So you can actually demonstrate for yourself like how this lensing effect works. If anyone's drinking wine tonight, this is one of my favorite demos to do. I recommend emptying the wine glass. But then if you observe a source of light, like a candle flame, one of these light bulbs might work as well. And if you align the bottom of your wine glass perfectly with this source of light, you get something like we have in the bottom left image here. We call this an Einstein ring. This is a perfect circle. And this is because your wine glass is symmetric and you've perfectly aligned it with your light source. Things in space don't tend to be symmetric or perfectly aligned. So what we see in real life is more like the two things on the right, where you see something kind of at an angle or not exactly aligned, and you get these characteristic arc shapes that will tend to follow around the edge of a ring. You get multiple images. You can see in the bottom one that there are three images, because you can kind of see the one in the middle. The one in the top, there are probably five, but because the...
So normally with a painless space... You're not supposed to say
choo-choo. Yeah. So I was just saying to someone earlier that I'm still completely fascinated by American trains because they're so long. It's amazing.
Don't write on them.
So what was I talking about? Gravitational lensing, arc shapes. So if you want to observe these kinds of things in real life, this is the kind of shape you want to look for, things that are kind of stretched out into this arc, and in fact we call them arcs, or strong arcs, or lensed arcs. Alright. So, at the time that Zwicky proposed using gravitational lensing to observe distant things, it was all completely theoretical, because nothing like this had ever been seen. And it was, a lot of people said, in fact Einstein himself said, this is a nice idea, but we'll never actually see this, because these things are going to be way too faint to actually see with telescopes. Everyone throughout history tends to underestimate technological development. So I'm hoping this is still true, and we'll be exploring distant extrasolar planets within my lifetime. Probably not true. But the thing that was a complete game changer was that the technology we used to observe objects through telescopes changed rapidly during the 20th century. So at the time that Zwicky was writing, right up until the 1980s, all observations were made with photographic plates. So this is an image taken on a photographic plate in 1888 with an 8-inch telescope in Cambridge, Massachusetts. Does anyone know what this is an image of? That's pretty good. I wouldn't have known that if I didn't download this image. It is the Horsehead Nebula. Photographic plates tend to have a very wide field of view, so you need to zoom right in there's a kind of dark region here. You see around about there that's darker than the rest, and that is the Horsehead Nebula. So in the 1980s, everything changed when CCDs were introduced. These are charge-coupled devices. They form the basis of what we now call digital cameras. So they were discovered pretty much by accident. Some people, I believe it was Bell Labs, were trying to work on memory storage devices, and they discovered something that was incredibly sensitive to light, and this was not really what they were trying to do. But astronomers jumped on it and said, that's awesome, you've invented a really sensitive light detector, this is what we want. So you can thank astronomers for having cameras in your cell phones. In 1999, this image was taken with a CCD fitted on the Canada-France-Hawaii telescope, which is in Hawaii. This was in 1999. This same field, it's obviously much more zoomed in because the field of view is a lot smaller. This is the Horsehead Nebula. And you can see already the level of detail you can get with a CCD is so much better. So this was a complete step change in astronomy, and enabled us to push way further out into the universe than we were ever able to before. Just for fun, this is another image of the same thing taken in 2011. So we're still improving technology, and every time a new bit of technology comes out, you can see that science just changes. It's pretty amazing. So with the advent of CCDs, for the first time, it was actually possible to observe these gravitationally lensed arcs. And does anyone know which cluster was first, in which cluster a gravitationally lensed arc was first detected? No, this is another one that would have been trivially easy if you'd already seen the talk. No, it's called Abell 370. This is the image. It was observed with the Canada-France-Hawaii telescope in 1985. And it was actually simultaneously discovered by two groups. This was the first one that actually made it through to publication in 1986. And the thing that we're interested in is this thing here. See, like the long stretched out arc. That's actually a galaxy, just one galaxy, not too different from the Milky Way, but really, really far away. It happens to lie behind this cluster, so all of the light has been stretched out and distorted into this huge arc shape. And if I show you a fancier image, this is one taken with the Hubble Space Telescope many years later, you can see why this particular galaxy is known as the Dragon. The red color it has is because it's very far away. It's far behind the cluster. All of the kind of bright orange things you see in this image are cluster galaxies, which I don't care about. I just care about the mass of the cluster. I would be ecstatic if we could have galaxy clusters that were just dark matter, but alas. It does make the images a bit prettier. As you'll see later, the images of the galaxies I actually work on, they're not going to make any fancy press release. So this was a huge revelation in the 1980s, that we actually can see gravitationally lensed galaxies. And the reason galaxy clusters are so useful for this is clusters of galaxies can be collections of thousands, even tens of thousands of galaxies. So they're the most massive gravitationally bound structures in the universe. And the more mass you have, the more lensing you can do. So you can see very, very distant things by using this gravitational lensing effect because of the magnification. The magnification works in two ways. It gives you more light from the distant galaxy, but it also stretches the galaxy out. So you can see in this case, you can kind of see the disk of the galaxy down here. You have to squint when you're looking at images of very distant galaxies, but trust me, that's a spiral galaxy, and it's just one of the spiral arms that's then being swept out into this huge arc. So you can see this in way more detail than you would ordinarily be able to see a galaxy that's this far away, because it's been magnified and stretched out so much.
What's the red shift on that?
I was just trying to remember that. It's something like 2. So we're talking like 75% of the way back to the Big Bang. But I could be wrong on that. So this was in the 1980s. Not this image. This image was from the last decade. but the discovery of the galaxy was in 1985. For the first time in the 1990s, a normal galaxy held the record for the most distant object ever observed, and that was this guy here. MS 1358 is the name of the cluster. These clusters all have incredibly boring names. I often say astronomers should not be allowed to name anything. So the animation you're watching is just a fly around of the cluster. The image on the left is a zoom in of the lensed galaxy. So the big round thing is just a foreground cluster galaxy, and the thing with the square around it is a distant, a galaxy behind it that's been stretched by gravitational lensing. Now this one is at a redshift of 5, so we're now like edging towards the first billion years of the universe. And this was the first time since the 1960s, when very far away quasars were first discovered, the first time that a normal galaxy held the record for the most distant object that was known. This was in 1997. This galaxy is a very good friend of mine. It featured in my PhD thesis. I was looking at the star formation and gas content and stuff, and all things that you could never normally do at a galaxy that far away, but you can do because of the magnification, which is really cool. Yay!
Is it actually opening there? Going down across.
Really?
It's coming.
These events are always so quirky. It's fun. If I talk over this, I'm relatively quiet, so yeah, alright. So this was 1997. We had our first distance record since the discovery of quasars that was a normal galaxy. And what was the next revolution in the field of high redshift astronomy? Does anyone know? This wasn't one of our questions. This is just interesting. So the thing that led to the Hubble Deep Field, Gotham mentioned at the beginning of tonight, was the last servicing mission to the Hubble Space Telescope. And this was a huge deal to me. This was in 2009. Because one of the instruments that they installed on the Hubble Space Telescope was called Wide Field Camera 3, or WFC3. Again, astronomers should not be allowed to name anything. And this completely revolutionized this field because it's an incredibly sensitive camera that looks in the near infrared. It also does the ultraviolet, which I don't care about. Very distant galaxies are invisible in the ultraviolet, so I'm like, why would you take a picture of blank sky? I don't care. But the near infrared is really, really crucial because these galaxies are so far away that the expansion of the universe has stretched all of their light out into the red end of the spectrum and actually beyond the range that we can see, so into the near infrared. And this means that if you want to look at things far away, it doesn't matter how good your optical telescope is, you're never going to see them. So this is why we need this very sensitive infrared camera. The next step change in this field is going to be the James Webb Space Telescope, because not only is it bigger and more sensitive, it actually looks even further into the infrared, and that's the thing currently that's limiting us, looking even further away. So WFC3 in 2009, huge deal, and one of the most famous results that came out of it was the ultra deep field. The ultra deep field is really amazing. People don't appreciate what a cool image this is. I think it's the best photograph ever taken by mankind. A long way above any picture of Kim Kardashian. Just to give you a sense of perspective of this image, if you were to take out a penny and hold it at arm's length, then the eye of Lincoln or the Queen, depending on where you are, would completely cover this patch of sky. And in this image, there are about 10,000 galaxies. So there's a couple of stars. You can see like that one there is a star, but pretty much every other speck of light here is a galaxy. So every one of these little dots has billions of stars in it, and yet you could fit all of these in an eye on a penny. I think it's pretty incredible. And some of these galaxies are the most distant ones that we know of, because they've been observed as far red as we can go, and this is the deepest image we've ever taken. There have been updated versions of this since, but this is still pretty much the standard. It involves staring at this one tiny, tiny little patch of sky for about a month. And you've got to remember, the Hubble Space Telescope is orbiting the Earth, so it's moving around 17,500 miles an hour, and yet it can stare at this tiny, tiny patch of sky completely steadily for a month. I think that's pretty incredible. It's got to be like the greatest feat of engineering that we've ever accomplished. But it's still not good enough for me. So the obvious question, once we've got the Hubble Ultra Deep Field, is what would happen if you had an ultra deep field plus lensing? So this is what I now work on. This is the Frontier Fields program. And the idea is to do just that. We're trying to get the Hubble Ultra Deep Field, but with lensing. So we do this by taking really deep images of galaxy clusters to see the galaxies behind them. So 6 clusters were chosen for this program. This is roughly where they are on the sky, related to constellations. One down here is Abell 2744. This was the first Frontier Fields cluster. Number 2 down here is Max 0416. You'll notice that Max 0416 is behind the Eridanus constellation, which is also where Vulcan is in Star Trek. And I just have to say that so I can equalize my Star Wars and Trek references. So those were the 2 first-year clusters. They were completed just over a year ago. Clusters 3 and 4 were Max 0717 and Max 1149, both in the Northern Hemisphere. And we've just started collecting data on 5 and 6, which are Abell 370. So our very good friend, who was the first lens ever detected, is now getting super deep imaging, and Abell S1063, I believe. I can't read that, yeah. That's one we haven't actually got data for yet, but should be completed by this summer, so this is still ongoing. The way this program works is making use of the fact that we have multiple instruments on the Hubble Space Telescope, and you can use them simultaneously. So this is the field of view of the Hubble Space Telescope, and the 2 instruments we're interested in are ACS, which is this square here, that's the advanced camera for surveys, and WFC3 in the center there, Wide Field Camera 3. So Wide Field Camera 3, I already mentioned, looks in the infrared, and ACS looks in the optical. And it's important to have both of those because I mentioned the distant galaxies have all of their light pushed into the red. The only way you can know something is a distant galaxy is if you see all the light is red and it's completely invisible in the optical. So even though we don't expect to see anything that I'm interested in the optical, you still have to have it to prove that your galaxies are far away. So it's using both of these instruments together that gives us the power to look at faraway things. What we do is we point one of these cameras, so in this instance Wide Field Camera 3 at our galaxy cluster. This is Abell 2744 on the left. And then at the same time, ACS is looking in the optical at a blank bit of sky about 5 arc minutes away. So we're getting our imaging of our galaxy cluster, and then pretty much for free, we get an extra Hubble Ultra Deep Field without our lensing, only a little bit of lensing, a little way away. And then because of the way that Hubble works, you wait 6 months, the telescope flips over, and now you can do your optical imaging of the cluster and your infrared imaging of this blank field. So we now have optical and near infrared in both the cluster and an associated, we call it parallel field. So to give you an idea of what we're looking for, this is a silly little animation I made of the Whirlpool galaxy, and we're going to move it very, very far away to about 75% of the way back to the Big Bang and put it behind this galaxy cluster. So you can see already the light has bent it, so it's all the way over here. It's now racing behind the galaxy cluster at trillions of times the speed of light, and you saw as it got directly behind the cluster, it went berserk and produced all of these multiple images and gigantic arcs. So if I do that again, So this is the exact position it is when the cluster is introduced, and it's just the light being distorted that pushes it over to the side. And as it moves, you can see as it goes past this first foreground galaxy, it gets a little bump, and then it goes berserk. So that's the point at which we're really interested, because it is incredibly magnified at that point where it's directly behind the galaxy cluster. So this is the real image of what Abell 2744 looked like when we got all of this super deep data in. And I'm going to tell you right now that anything you can see in this image I find intensely boring. Still makes a pretty picture though. All of the orange things are going to be cluster galaxies. So these are really, really close by my standards, you know, only a few billion light years away. Anything you can see that's kind of stretched out and elongated is going to be a distant lensed galaxy. So let's see if we can see any. There's this one here, kind of purple dude. Some up here, you can see it kind of elongated and stretched out. These are all going to be background distant galaxies that have been lensed by the cluster. But like I said, anything you can actually see with your eyes, way too close for me to be interested. So the things I'm interested in, things like this. This is a galaxy which is about 95% of the way back to the Big Bang. And it looks a bit like a blob. So I'm going to tell you, this is an incredibly bright galaxy. This is like one of the best images I could ever have hoped to get. And there's another one. And another one. So a weird thing that we didn't expect to find is there appears to be like the beginnings of a cluster of galaxies behind this foreground cluster that's forming in the early stages of the universe. So when the universe was only 5% of its current age. And this is pretty amazing. It's not a thing we expected to see. It's giving us, because these galaxies are so bright, trust me, they're bright, we can see them in way more detail than we ordinarily would expect to see galaxies that far away. So, and the reason we wouldn't expect to see this is the volume you're looking at is really, really tiny. You've got to remember that this whole field is very tiny. It's about the same size as the ultra-deep field I showed you earlier, so you can fit it in Lincoln's eye if you're holding it that far away. And also, because the area has been magnified, if you actually trace it back to the beginning, it's even smaller. So in an area that small, you don't expect to find things that are rare, and bright galaxies are rare. So finding bright galaxies in a small volume is a huge stroke of luck, or we don't understand how common they are, but let's not go there. So the second cluster, this is MAX 0416. You might notice some of these look a bit like train wrecks, not like nearby clusters you might have seen. The reason is that they're actually merging clusters, and we think this is two clusters that are in the process of merging together. This makes them hugely massive and really good lenses, so it's good for our purposes. This one has some really spectacular lens galaxies. You can see this one along the top, and all these ones in the middle. And there's one that appears to go like from here all the way across here. Again, way too close for me to be interested in them. But we have some other galaxies behind this, and I'm only picking out my favorites. There's actually about 100 very, very distant, so more than 95% of the way back to the Big Bang galaxies behind each of these. So this one here is one that is even further back than the ones I showed you before. We're talking like 96 to 97% of the way back to the Big Bang now. And again, this is a pretty bright galaxy. This is a super bright galaxy, and this one as well. So this is really pushing the limits of what we can do. If you try to get much further back than this, all of the light is being pushed beyond the wavelength coverage that we have, even in this infrared camera. So this is why we need James Webb. James Webb will enable us to see even more distant things. So the other problem we have when we're doing this is we're using the galaxy cluster to magnify our distant things, but the galaxy cluster itself is in the way. The cluster is producing huge amounts of light, and this makes it very difficult to see any small faint things that might be behind it. So if we move to our third cluster, this is MAX 0717, I'm going to show you one of our distant galaxies. Can anyone see it? It's in the center of that box. You can't, because it's very close to one of the foreground galaxies. So what I've spent about the last year of my life doing is developing a method for modeling and subtracting all of the foreground stuff so you can get a better view of the things behind it. And so this is an example. You can now see that, again, trust me, that's a really, really bright image of a galaxy. So we can actually push even further to the limits of the very faintest things that we can see. We're hoping to have a press release on this out within the next month or so. So I just wanted to finish with the most recent imaging that we've got in, where we found something really cool and unexpected. And I'm using the word "we" loosely here because this is not about galaxies. It's more related to what Gotham does. This is MAX 1149. This was the fourth Frontier Fields cluster. I know this cluster very well. It featured in 2 chapters of my PhD thesis. And the reason for that is one particular lensed galaxy in this image, which by my standards today is really nearby, but it's actually more than halfway back to the Big Bang. And there's 3 images of this galaxy in this cluster. There's one up here, one down here, and one in the middle there. And if I move the circle so you can see it better, if you look at this one, just above the star, because that's the most magnified, if you squint a bit, you can convince yourself that's a proper spiral galaxy, right? That's like some of the glossy images you would expect to see from the nearby universe from Hubble. You can see a bulge, you can see spiral arms, and they're a bit distorted because they're lensed, but it's a proper spiral galaxy. But this is more than halfway back to the Big Bang. And the reason we can see it is it's magnified, but it's magnified in a really weird way. Instead of being stretched into a long, thin arc, it's stretched equally in both directions. So it's just like you've zoomed in on your computer and blown it up to a larger size, which is really, really amazing. So you can do all kinds of stuff with this galaxy. And the things that I did in my PhD thesis were looking at the individual star-forming regions within the disk of the galaxy. You can look at the dust distribution, the ages of stars, how they're distributed, which gives you an idea of how the galaxy formed. I looked at the dynamics. You can see how the individual stars are moving to get how fast the whole disk is rotating. It's incredibly cool. But one thing we didn't expect to find was completely by chance, when the Frontier Fields imaging was taken, a supernova went off. So if you look in, this one spiral arm is wrapped around this foreground cluster galaxy in such a way that you get 4 images, the 5th one being behind the cluster galaxy so you can't see it. And you can see they're very conveniently highlighted with arrows. The 3 you can see really clearly. This one you might have to squint a bit on the bottom. But that's 4 images of a supernova that just happened to go off when this image was taken. And what's really cool is I just showed you that this whole galaxy is imaged 3 times in this cluster. So that means that we should see this supernova go off in the other images as well. So it turns out the one way up at the top is first. So we zoom into this one here. Ooh, that's simulated, we didn't actually see it. And then we move to this one down here. This had already gone off when the image was taken, so it's already there, but you can see the simulated explosion going off in 4 places. And then there's a 3rd one right in the center. Ooh. So we should expect to see this supernova in this this other image of this galaxy right in the center of the cluster after the one we've already seen. So when this the quadruply imaged one was first observed, there was a massive rush to look at the lens models and trying to figure out when we should expect to see this next reappearance of this supernova. And the estimates were they were pretty good. You can constrain it pretty well because a lot of people have done work on modeling this cluster, and you can work out the path differences the light has to take and therefore the time delay. They worked out that that first one should have appeared around 1995, so sadly it's too late for us to go back and see that. But then this 3rd one in the middle, they originally said should be somewhere between 2015 and 2020, and gradually those got narrowed down to somewhere in 2016, and the best guess was first quarter of 2016. So only a couple months ago, I was giving a talk where I made fun of these people And I said, oh, they're just saying this to get telescope time. You know, once we hit the first quarter of 2016, they'll say it's going to be the next quarter and then the next one, so they can keep having Hubble time. They proved me wrong. They got imaging in December of 2015, and this is not as deep imaging, so you have to use your imagination a little bit. The image on the top right is from October 30th. You can see there's nothing in that circle. The one underneath it is from December 11th, and there is definitely something there. So the lens modelers actually did a really good job of predicting the return of the supernova. And it's pretty amazing that this is a survey that was not really designed to find these things. No one expected it. And it's a really, really cool side effect of gravitational lensing and really proves that science works. So with that, I want to say thank you very much for listening.
We've got plenty of time for questions, and we've got some for our speaker.
You mentioned Zwicky, and he postulated dark matter. Please tell us about Vera Rubin and dark matter.
Okay, the question was, I mentioned Fritz Zwicky postulating dark matter. You wanted to hear about Vera Rubin. So the thing that Fritz Zwicky did is he was looking at galaxy clusters. And if you look at how quickly galaxies are moving within their clusters, it doesn't make sense that they're sticking together. Like, they're moving fast enough that given the amount of mass in a galaxy cluster, they should fly off in all directions. So there had to be more mass there that we can't see, it's dark, that was pulling them all in. So this was in the 1930s. Sometime later in the 1970s, Vera Rubin was looking at the movement of stars within a galaxy. So instead of individual galaxies in a cluster, this is now stars within one galaxy, and looking at how quickly they're rotating. And she found the same thing, that they were moving way more quickly than you would expect. So the stars on the outer parts of the galaxy should be flying off, and they're not. They're somehow bound to the galaxy. And therefore, there has to be more matter there that we can't see. Which was an incredible result, and she's still alive, and she completely deserves a Nobel Prize for that. I hope they'll one day recognize her. Oh, the question was, what telescope did she use? I actually have no idea. You know, it was a quick peak 4 meter. Okay, a local one. Yep.
Another history note: that black and white lens and Petrosian image was taken at Kitt Peak as well.
Oh, okay. The image I showed of ABAR 370, the first gravitational lens dark, was also Kitt Peak. I'm from Texas, so I don't know the local history. I'm sorry.
Not only that, you actually ran into Roger Lens today. You didn't even realize it was him.
Oh, really? Oh, I didn't know that. Yep.
When I first heard a talk about using gravitational lensing for astronomy about 25 years ago, I thought, well, that's ridiculous. How much of a coincidence would there be for a galaxy properly positioned behind a cluster for this to happen? It would be a very rare event, but it seems to be quite common. Now, is that because the early universe is so closely packed, because it's so much smaller, that we see a lot of this?
The question was that when people first started to talk about using gravitational lensing for astronomy, it seemed really unlikely, but it now turns out to be really common. So what's interesting is, even when I started doing this, which was only a decade ago, it was still a really kind of niche, out there, weird thing to do. And it's now completely routine, and people do it all the time, and it's taken seriously, which is awesome. Never thought I would be taken seriously. So the reason it's really common, I think, is just that our images have got really deep. So you look at something like the ultra deep field, it's a blank bit of sky with nothing in it. But if you look hard enough, there's always going to be something, because the universe is really big and it's got lots of stuff in it.
But the early universe is small.
The early universe is small, but your cone is getting bigger, so you're covering more volume the further away you get. You just have to look a lot harder, much longer integrations to be able to see the very distant, very faint things. So I don't know if you've seen simulated images of what James Webb will be able to see. What I find really interesting is if you show these to a public audience, they say, oh, that looks worse than Hubble because it looks really noisy. But actually it's just that it's so much deeper than in all where Hubble has these just black voids, James Webb finds things. So there's like little specks that look like noise but are actually things. And I think that's amazing. I'm really excited to see that. Yep, at the back.
So you showed a couple of galaxies that were really, really far back. Now with the gravitational lensing model, can you find out where they're supposed to appear? They're like after second image on the other side of the lens?
Yes, so the question was, I showed the faraway galaxies, and can I predict where the multiple images should be? And yes. So with the frontier fields in particular, this is really the first time we've had multiple teams modeling the mass of the same clusters. So what's really interesting is you can now look at lots of different people's models that use different assumptions and use each of them individually to work out where the multiple images would be. And then you go hunting around that position to see something. Gravitational lensing doesn't affect color at all. So you should see a galaxy with exactly the same colors around that position. Turns out it's really hard. The people who do this for a living are usually doing more nearby galaxies because they're using them to constrain the mass distribution. But even they make mistakes. They identify things as multiples that really aren't. So when you get to these really, really far away things where you're much less certain of what the colors are, identifying the correct multiple images is really, really difficult. But it can be done. And we do have some where we think we have several of the images. Anyone else? You're also welcome to accost me over beer if that's easier. I drink cider, by the way. Yep.
So is gravitational, so right now we're talking about a lot of gravitational lensing with really large objects like galaxies. Is it possible to get sensitive enough to actually image extrasolar planets or something like that using lensing?
Oh, okay, this is interesting. The question was, is it possible to get sensitive enough to image extrasolar planets with lensing? So this is actually one of the cool new methods of detecting extrasolar planets using microlensing. So the thing I do is strong lensing, which just means it's lensed a lot. Microlensing happens when a planet passes in front of a star. So not like a transit where it's very close to that star and it's blocking it, but a microlensing planet could even not be associated with a star, it just happens to pass across the line of sight. And because the light from that star is now going past a planet, it gets magnified. But planets are very, very small, so it's magnified a teeny tiny amount, hence microlensing. And people are doing really, really cool stuff with that now to actually detect extrasolar planets, which is pretty awesome. So, is there anyone else?
If we don't have any other questions, we can thank our speaker. She's going to be around here for a while anyway to answer more questions. So let's give Rachel a big round of applause.
Thank you very much.
So if you answer trivia questions, don't head out yet because we have stuff to give you.
Okay, so the first question, the people who answered correctly, and I will not look at what I'm doing, is, let's see if I can read handwriting. Team Arya and Rosalinda?
Team Anya and Rosalinda!
Okay. Okay. Now, stay there. Okay. Now for the second question. Okay, yes, making sure that we got all the correct answers here. Brian Ruth.
fiber optic cables and crispy.
Thank you.
Okay, now number 3